Okay, I think the recording starts. You know what? This Monday, this class is doing the paper presentation, and out of 3 presentation, 2 of them are yours.
Oh, wow.
I think yeah, it should be here.
I'm basically going to cover those 2 papers overview in this talk.
Yeah, sure. Feel free to arrange your talk. It's your talk. One student outside. I think we can start now. Most of the students here, and I will keep eye on the participant and allow them to join.
Sure.
Okay, so let me start with a brief introduction. Here. So hello everybody. Today we are really happy to invite Rashmi to give us a talk on accelerating homomorphic encryption. And Rashmi is a research scientist at Boston University and a visiting scientist at MIT. She received her doctorate in computer engineering from Boston University in January 2023. Congratulations. And during her doctoral studies, she focused on hardware acceleration of post-quantum cryptographic schemes and fully homomorphic encryption. She received Best Paper Award at GLVLSI 2020 and ICCD 2020. She was recently selected for the EECS Rising Star Workshop at Georgia Tech. After receiving her doctorate, she worked at the Intel Labs in the Security and Privacy Research Group. So take it over.
Thanks for the kind introduction, Dee. Yeah. So, hello everyone. I'm going to present my work on affordable and practical acceleration of CKKS-based fully homomorphic encryption that was basically done as part of my PhD. So this talk consists of 2 parts. First, an architectural analysis of the CKKS scheme, along with the discussion on several memory-aware design optimizations that we came up with, and with like all the recent ASIC developments that took place in the past year or so, this work is like very relevant. So I'm going to focus more on that perspective as well when I go through the slides. And the second part of the talk is basically the design of our FPGA accelerator that we call as FAB. And FAB accelerator implements packed bootstrapping for the first time ever on an FPGA for practical and secure parameters. One thing I would like to mention is, please feel free to interrupt and ask questions, as the talk is like very technical and may start to feel a bit overwhelming. So feel free to interrupt and ask questions. So let's get started. Fully homomorphic encryption, as you all know, has emerged as one of the powerful cryptographic tools to enable privacy-preserving computing by allowing computations over encrypted data. Therefore, in scenarios where private data needs to be uploaded to a third-party cloud server, fully homomorphic encryption enables cloud operators to perform complex computations on encrypted user data without ever needing to decrypt it. And the result of such fully homomorphic encryption-based computation is in an encrypted form and can only be decrypted by the data owner. So the server has like no access to the secret key. Only the client or the data owner owns the secret key. So that's the basic concept behind fully homomorphic encryption. So after Gentry's seminal work in 2009, several lattice-based fully homomorphic encryption schemes have been proposed. Few of the recent and most commonly used schemes can be classified into two different compute models. First model takes a word-wise approach, allowing direct encryptions of integers and floating point numbers. Schemes like BGV, BFV, and CKKS fall into this category. And the second category performs bitwise operations and includes schemes like FHEW and TFHE. So in this work, like we focus on CKKS scheme as it allows operating on real numbers or more specifically fixed point numbers and naturally fulfills the requirement of many real-time privacy preserving applications. And the basic data type in CKKS scheme, because of the underlying ring learning with error encryption scheme, consists of vectors of length n, where each element in the vector is of log qubits. So given a real number, first step is to encode it into a plain text vector of length n. Then we scale it up by using a scale factor delta to preserve as many precision bits as possible. And then we encrypt this plain text vector by adding some random noise to generate the ciphertext, which is actually a pair of polynomial of length n. And each element in this vector is of log qubits. So that's the basic data type in CKKS scheme. And the basic building blocks in CKKS scheme consist of 6 operations, which are listed here in this table. The first operation is PT add, which stands for plain text add. It adds a plain text vector to an encrypted vector. Then we have add that adds two encrypted vectors. So these are like straightforward element-wise modular addition operations. Then we have PT mult that multiplies a plain text with a ciphertext followed by a rescale operation, as you see here. And next is mult that multiplies two ciphertexts followed by a key switch and a rescale operation. Then we have rotate, which rotates the slots within the ciphertext by a given index k. And finally, conjugate, which is also a special form of rotate operation. And as you can see here, both rotate and conjugate also need to perform the expensive key switch operation. So I'll talk a bit more about rescale and key switch operations in the following slides, just to give you a high level idea of how these operations work. So rescale, or also known as mod down operation, is to handle the growing scale factor. So in CKK scheme, as we just saw, that we scale the plain text by some value delta before encryption. And this delta grows during homomorphic operations. Say, for example, if we want to multiply encrypted x and y, during multiplication, we also square the delta value. So with one level of operation or one level of multiplication, this is not a problem. However, when we perform subsequent homomorphic operations, the scale factor itself grows beyond control, destroying the underlying message. So thus, rescale is a way to deal with this growing scale factor. So as using rescale after each multiplication, we basically divide the ciphertext by delta, so that delta square becomes delta again after each multiplication. Next is the key switch operation, which is a critical operation and the most expensive one as well. And a simplistic way to look at the key switch operation is as follows. So if we have a ciphertext that is generated using the key mentioned here, when we rotate the ciphertext by 1, and try to perform the decryption operation, we cannot decrypt the ciphertext using the same key that was used for encryption, because we have rotated the underlying plain text slots in the ciphertext. So instead, we need to have a key that is also permuted in the same way. So if you see here, now we permute the key also by 1. Then after rotation operation, we will perform a key switch operation to now have the ciphertext encrypted under this new rotated key, so that when the decryption is done, we can still recover the underlying message correctly. And the sequence of operation that takes place in key switch operation are we first perform decomposition, mod up takes this ciphertext, which is in Q basis, and raises the basis to PQ. And then the inner product between the ciphertext limbs and keys happens in this raised basis, followed by a mod down operation that reduces by P to bring the ciphertext back to the basis Q. So having understood this, the basic operation, let's look at some of the challenges with FHE-based computing. So as we perform various homomorphic operations, the underlying noise, which was added during the encryption process, begins to grow. For example, add will double the noise and multiplication will square the noise. So to tackle this noise growth and prevent the underlying data from getting corrupted by this noise growth, we need to use large parameters and need to perform an expensive operation known as bootstrapping. To perform efficient modular arithmetic operations on these large elements, RNS decomposition or residue number system decomposition technique is typically used, wherein if we break down our large Q to smaller Q primes that are typically machine word sized, implying that our one large ciphertext will decompose into multiple ciphertexts with smaller coefficients. These decomposed ciphertexts are more commonly known as the limbs of the ciphertext, which is 3 here for the example, which is shown on the slide. Coming to the second solution, that is bootstrapping. So bootstrapping operation tries to refresh the noise in ciphertext by performing decryption homomorphically. And it is expensive than the primitive addition and multiplication operation, as it needs to perform thousands of these addition, multiplication, and rotation operations. So the first CKKS bootstrapping implementation took about 8.7 minutes on a CPU. And with developments over the past 3-4 years, one of the recent GPU implementation reduced this bootstrapping time by 350 times, bringing it down to 1.5 seconds. However, the same work observed that when performing an end-to-end application evaluation like logistic regression model training, about 50% of the runtime is spent in bootstrapping. Hence, there is a need to further optimize the bootstrapping performance, and therefore several hardware acceleration efforts have been ongoing. And to quickly show you the current hardware acceleration landscape, so we begin with one of the first FPGA implementation of CKKS scheme known as EECS. Although they did not implement bootstrapping operation, they sort of provided a good starting point. And then in 2021, the first ASIC proposal, namely F1, got published. It implemented bootstrapping, but unpacked in the sense that only one slot of the ciphertext was used. Then 3 other follow-up ASIC proposals came up that were using more practical parameters and performed packed bootstrapping as well. So one thing to note here is that none of the ASIC proposals are fabricated into or manufactured into real chip as of now. Then let's now spend a few more minutes comparing and contrasting these works, right? So on this first plot here, we have the scheme parameters and the bootstrapping runtime. So if you look at this plot, F1 has the smallest parameters and the least bootstrapping runtime, but it is not much useful due to the support for small parameters and unpacked bootstrapping. Like only a single slot of the ciphertext is used in this implementation. Then out of the remaining 3 implementation, ARC has the least bootstrapping runtime with practical parameters. So however, due to difference in parameters, it is not fair to compare the bootstrapping runtime in a straightforward way. So what we do is we go ahead and compare the bootstrapping throughput, which is defined by the equation which is given here, right? It takes into account the differences in the slots and the levels of operations that can be performed during bootstrapping. So we see that on this plot that ARC is able to achieve a better bootstrapping throughput as well. However, the problem is that to obtain this high bootstrapping throughput, these ASIC designs implement tens and thousands of modular multipliers and make use of large on-chip memory. So fitting these large resources requires moving onto expensive, more recent technology nodes, which is 14 nanometer or 7 nanometer. And all of these ASIC proposals result into large chip area. And these large chip areas translate into tens of millions of dollars of fabrication cost. So with such a high cost, these solutions are not very affordable. Therefore, we need to come up with practical solutions that are affordable. And one way to do this will be by reducing the size of on-chip memory to say 32 or 64 MB at max. However, as soon as we do that, we end up accessing main memory more frequently. Thus, we need to balance the hardware design solution by only having as many compute units as required to keep up with the data accesses from the main memory. So with these two limitations in mind, we propose two practical and affordable solutions. First, we propose several memory-aware design optimizations that are agnostic of the underlying compute platform and can take advantage of small, say around 32 MB on-chip memory to accelerate the bootstrapping operation. And second, we propose a full system implementation that is fab, which makes use of FPGA compute platforms that are readily available in cloud environments and are inexpensive. So to completely understand the performance bottlenecks in the CKKS bootstrapping operation and to look for acceleration opportunities, what we did is we first developed an in-house simulator called a SimFHE. It is a simple Python-based custom functional simulator that lets one set the scheme parameters as well as the architectural parameters like number of functional units and parameters related to memory subsystem. And then it keeps track of the compute and memory transfers happening within each of the primitive operations. And analysis using SimFHE reveals that all fully homomorphic encryption operations in CKK scheme exhibit a low arithmetic intensity, less than 1 operation per byte. And then an end-to-end application, which is built using these primitive operations, also exhibits a low arithmetic intensity. And our second observation is that at any given point of time, we need to maintain large working sets in on-chip memory to avoid frequent main memory accesses. So with a practical parameter set, the size of the ciphertext itself is about 73 MB. And in addition, we have other data to manage. So our commercially available platforms only have 30 to 40 MB last level cache that cannot accommodate these large data sets, which are like 73 MB or double in size. So if we cannot afford to have large on-chip memory, and we cannot avoid these frequent main memory accesses and increased orientation switch leading to increased memory bandwidth requirements. So let's quickly take a look at what's an orientation switch before we move forward. So in CKK scheme, there are two types of data access patterns, limb-wise and slot-wise. So there are operations like entity and inverse entity that need entire limb of data at once, as the slots within the limb need to interact, while there are operations like new limb that needs to work with same slots across different limbs at the same time. So with this requirement, if we take a look at the mod-up operation, it first performs inverse entity operation, which is a limb-wise operation. And now, because we do not have enough memory on chip to bring in multiple slots across all limbs for the next new limb operation, we need to write out the entire limb after inverse entity and then read slots to perform new limb operation. So thereby implying that a small cache will result into frequent change in data access pattern, resulting in frequent main memory accesses. Therefore, we propose several memory-aware design techniques by assuming an upper bound on the on-chip memory size that we have. And our goal is to reduce the DRAM reads and writes and reduce this orientation switch. So to this end, we present two categories of the optimizations. First are the caching optimizations that include several hierarchical cache optimizations, demonstrating best case utilization of various sized caches. And then we propose several algorithmic optimizations that include mod down merge, mod down hoisting, and key compression optimizations. So one thing to keep in mind here is that caching optimizations do not reduce the operation count. They only reduce the accesses to main memory, while algorithmic optimizations reduce the number of operations, in turn reducing the main memory accesses. Right? So let's look into the caching optimizations a bit more. So the first optimization is caching open limbs, wherein we consider that we have only 1 MB of on-chip memory available. So now if we want to perform a rotation on a ciphertext that has 3 limbs, naively we will perform automorph on all 3 limbs, requiring 3 reads and 3 writes. Then we will perform the next operation, that is decomposition, which will again require 3 reads and writes. And we can keep going in the same way, including many reads and writes. And our typical ciphertext will have, say, 40 to 50 limbs, where each limb may be 1 MB, given the parameter set, implying large amounts of data transfers from the main memory. So, however, we can do better by greedily computing as much as possible on a single limb before writing it back to the main memory. Very simple concept, but very useful in optimizing the fully homomorphic encryption workloads. So this requires performing the operations of several higher level functions on a single limb before beginning the same sequence of operations on the next limb. So now what happens is we read a limb, perform automorph, decomposition, inverse entity in one go. And as now we need an orientation switch for the new limb operation, we write the current limb to the main memory. And we continue in the same fashion for all limbs of the ciphertext, thus saving many intermediate reads and writes from the main memory. Next, we have 3 other caching optimizations that work with 3 different sized cache to enable further optimizations within the key switch operation. For example, caching beta limb optimization gets enabled with a 3 megabyte cache and enables caching of beta digit limbs during mod up and mod down operations. Similarly, caching alpha limb optimization makes use of 27 MB on-chip memory, enabling further optimizations. In both of these optimizations, alpha and beta have concrete numbers as they correspond to parameters within the key switch operation for the chosen parameter set that we were working for in this work. For different values of this parameter, we will need different sizes of on-chip memory. And then we have the reordering limb computation that builds on top of the alpha limb caching optimization by changing the sequence in which the alpha limbs are generated during mod down operation. And this is to avoid writing them out to the main memory once they are generated. Therefore, all the 3 optimizations listed here reduce the number of memory accesses during key switch operation. The benefits of various caching optimizations are shown here on the slide. On x-axis, we have different optimizations, and on y-axis, the amount of DRAM transfers in gigabytes. So as the figure shows, with each optimization, there is large on-chip memory which is available, thus reducing the DRAM transfers during bootstrapping algorithm for deploying the various optimizations which I just discussed. And as the number of operations remain the same during all of these optimizations, we see an improvement in the arithmetic intensity. And one thing to note here is that the DRAM reads and writes for the ciphertext decrease, while for the key switching keys, it remains constant because none of these optimizations reduce the key reads from the main memory. Next comes the algorithmic optimizations that will reduce both the computations and DRAM accesses. So the first
question about caching optimizations.
Sorry?
I had a quick question about the caching optimizations. So when you're looking at the different optimizations, did you consider how you could optimize for multiple levels of a cache? Whether that would be like an inclusion policy or any of those like multi-level cache optimizations?
So one thing that we have realized during our analysis of the fully homomorphic encryption workloads is that you don't really need to have a cache hierarchy because that will add an overhead. So this is more of like a flat architecture wherein you just have like one level of cache getting the data from the main memory. Does that make sense?
Yeah, that makes sense.
Okay. Are there any other questions? Okay, I'll continue then. Okay. So yeah, as I was mentioning, the next optimization, next is the algorithmic optimizations that will reduce both the computations and DRAM accesses. So the first optimization here is combining the mod down and rescale operation. So considering the homomorphic multiplication operation, this optimization merges the 2 mod down operations in multiplication. So the first mod down the first mod down reduces by P, and the second mod down reduces by delta. So now to merge these mod down operations, we must lift the poly add operation, which is in between the two mod down operations, to above this first mod down. And we can achieve this by lifting the polynomials to the modulus PQ. So thus making the two mod down operations adjacent to each other, which allows them to be combined. So thus we can reduce the ciphertext by both P and the scaling factor delta using a single mod down operation. And this in turn reduces the number of entities by completing the key switch operation in the raised basis. Yeah. And the next optimization is hoisting the mod down operation.
Sorry, Rashmi, I have a question for the previous.
Yeah.
This merge does not change the computational results, right?
Yeah, it does not change the computational result, correct?
Okay, so for example, then what is the setup on the leftmost? Is it a software implementation in some of the existing frameworks?
Correct. The first one, right? The nine, that's how the software implementations are.
Okay, got it. Thank you.
Yeah. And I have noticed that OpenFHE has actually implemented this optimization in their library.
Oh, got
So
it.
they have this one in place, yeah.
I see. Thank you.
What's the purpose of the polyadd operation during the multiplication?
So if you remember, or if you're familiar with multiplication operation, like you generate or you perform like 4 polynomial multiplications, and then you have to do an addition, right? To combine the two cross multiplication terms. And that is what is done by the polyadd, if that makes sense. Does it make sense? It's just part of the homomorphic multiplication operation. It's not related to key switch.
Okay, thank you.
Yeah, so coming back to mod down hoisting optimization. When we require to perform back-to-back rotation operations, this optimization is very helpful. So given the sequence of operations in rotate, if we need to perform, say, back-to-back R rotations, we can move the mod down operations from inside the loop to outside the loop, reducing the number of mod down operations that need to be performed. So basically, this is mathematically possible. It does not change the noise addition, which is done during or which happens during key switch, and gives mathematically correct results as well. And then there also exists a popularly used optimization that moves mod up and decomposition out of the loops as well. Therefore, when we combine the two optimizations, right, like moving the mod up out and moving the mod down out of the loop, instead of our mod up and mod down operations, we perform these operations just once, thereby reducing the number of orientation switches and the number of entity operations that are required to be performed during back-to-back rotation operations. Then the final optimization, that is compressing the key with pseudo-random number generator. And this optimization is a natural result of the observation that half of the key switching keys consist of truly random polynomials. So by replacing these truly random polynomials with pseudo-random polynomials generated via PRNG on chip, we can avoid shipping the large random polynomials to and from DRAM. Instead, we need to send only the short PRNG key to generate the pseudo-random polynomials. And figure on this slide now shows how various algorithmic optimizations impact the operation count and the DRAM transfers for CKKS bootstrapping. So again, on x-axis, we have optimizations, and on y-axis, we have DRAM transfers, as well as the operations. So moving from left to right on the plot, the arithmetic intensity starts to improve as each successive optimization is applied. Now we come back to our ASIC proposals and compare the performance of these optimizations to the prior ASIC proposals. So we used practical parameter set for our memory-aware design optimizations and achieved a better bootstrapping runtime in comparison to BTS because it uses similar parameters or almost similar parameters that we have. We next compare the bootstrapping throughput as well, and we observe that even when there is a large gap between the bootstrapping runtime in comparison to Crater Lake and Arc, the bootstrapping throughput does not differ by the same amount because all of the caching, because of all of the caching and algorithmic optimizations. And we are able to achieve this performance using fewer compute units and with 32 MB on-chip memory, leading to smaller chip area and about 5 to 7 times lower cost. Thus, to summarize this first part of the work, we performed an in-depth architectural analysis of the CKKS FHE scheme and observed that without a prohibitively large cache, all fully homomorphic encryption operations exhibit low arithmetic intensity, less than 1 operation per byte for practical and secure parameters. To address these memory bottlenecks, we propose several caching and algorithmic optimizations that aim to reduce the memory transfers and orientation switch. And our optimizations enable a practical and affordable CKKS bootstrapping acceleration by enabling at least 8 times higher throughput than small cache implementations and only 2 times lower performance than large cache implementations at 5 to 7 times lower cost. So now we'll switch gears, and so one of the key observations from the previous few slides is that the existing ASIC solutions use a very aggressive approach to accelerate FHE-based computing in the sense that they use large number of modular multipliers on chip memory, and thus they lead to large chips and incur a very high cost, not just in terms of fabrication, but also in terms of the efforts that are required. And we already know that the CPU and GPU solutions are inefficient with lack of modular arithmetic units. So with Fab, we wanted to explore if there is an opportunity to leverage FPGAs that are readily available and are inexpensive compute platforms to accelerate FHE operations. And we wanted to see if we can come up with a solution that can provide practical acceleration of fully homomorphic encryption-based computing by efficiently utilizing the limited resources on the FPGA board and still can outperform the existing CPU and GPU solutions. So with these goals in mind, we present Fab, which is a novel accelerator that supports all homomorphic operations in the CKKS FHE scheme for practical FHE parameters. Note that we restrict ourselves to somebody is requesting remote control of my screen. Is there a way to disable that?
Sorry?
So I'm seeing this continuously on my screen. You can see it.
Yes, I can see your cursor. Yeah.
And it keeps popping up when I decline it.
I think
maybe I'll move it down, yeah, and continue. I'll see if it bothers. Yeah. Oh no. Okay. Yeah, sorry, it keeps popping up. It doesn't go away.
Okay. Maybe you can maybe quit and restart it. Okay. Yeah, I think if you want to start your video.
Yeah. You can see the slides in presentation mode, right?
Right. Everything's good on my side.
Yeah, I'm again seeing the requests for remote control of my screen.
Okay, I can't. I
I think it's a setting. If you go to security settings,
Uh-huh.
there's a request.
So this keeps popping up.
Request.
There should be like a request for remote control.
Which one, sir? I didn't see remote control. Is it collaborated? Zoom apps? I didn't see. So you, okay, yeah, it's a little bit weird. What's to start? So we can't see anything, any actions on it. So now it's
For me, this keeps popping up, so I cannot move to the next slide.
Oh, okay. Maybe you can you want to present this slides without in the presenter mode. It's fine.
Let's try. I'll try to move this on the side and see what happens. Okay, so let's try to start the slide again. So what I was saying is that we restrict ourselves to n equal to 2 to the power 16 parameter sets here, as opposed to the previous work that used 2 to the power 17. And this is just to minimize the ciphertext movement between the compute units and in memory. And FAB work, it implements a bootstrapping operation. A bootstrapping operation for the first time ever on an FPGA. And FAB is highly resource efficient in the sense that it implements only 256 functional units, where each functional unit supports various modular arithmetic operations and exploits maximal pipelining in parallelism. And FAB makes efficient use of the limited 43 MB on-chip memory to manage the hundreds of MB working data set at any given point in time. So to this end, FAB leverages various microarchitectural level optimizations, and I'm going to go through a few of them over the next few slides. So first is the functional units. So the functional units in FAB are tailored for the FPGA implementation to reduce resource overhead and improve latency. So to make efficient use of high performance multipliers and adders in DSP blocks, what we did is we use multi-word arithmetic approach that splits our 54-bit limbs to 18-bit operands for the multiplier and 27-bit operands for the adder. So FAB efficiently utilizes these functional units through fine-grained pipelining and by issuing multiple scalar operations in a single cycle. Then FAB also makes use of a novel modular reduction algorithm, which, unlike other modular reduction algorithms, avoids performing any multiplications. Instead, just uses shift operations, making modular reduction operation very resource efficient. Then FAB consists of multiple register files. The total capacity of all the register files together is 2 megabytes, and the register files are spread across the design and are used by the functional units, the address generation unit, and the control units. And each register file has multiple read or write ports with the same cycle access latency. And register files are used to store pre-computed values, system parameters, and intermediate polynomials that are generated as part of the various operations. Then coming on to the on-chip memory organization. So we used the Alveo U280 FPGA board, and this board has two types of on-chip memory blocks, the ultra RAM blocks and the block RAM blocks. So ultra RAM blocks are called URAM blocks in short, and block RAM blocks are called VRAMs. So the URAM blocks are 72 bits wide and 4K deep, and they can be used as a single port memory. The BRAMs are 18-bit wide and can be used as both single and dual port memory. So FAB uses a combination of the single and dual port memory banks that are constructed using URAM and BRAM blocks, providing a total capacity of about 43 MB on-chip memory. So as our limb bit width is 54 bits that I was mentioning earlier, we combine 3 URAMs together to generate 216-bit wide location, and then use it to store 4 54-bit coefficients in one location. And we arrange 64 such blocks in parallel to enable access of 256 coefficients at the same time. And this is pretty much to match the input and output count of the functional units. And this combination is denoted as a single bank that we can that can store like 16 ciphertext limbs, and it ends up consuming 192 URAM blocks. And we arrange the available URAMs into 3 banks as per the ring elements to obtain C0, C1, and a miscellaneous bank. And similar approach is used for BRAM, with the only difference that now as we combine 3 BRAM blocks, we get only 54-bit wide location. So instead of storing like 454-bit coefficients at every location, we are storing just one 54-bit coefficient at every location. So now as we have understood the memory organization, we take a look at the key switch data path modification, which was one of the main contributions of this work. So through this optimization, we could schedule and reorganize the sub-operations in key switch to manage about 112 megabyte of data, which consisted of about 28 MB ciphertext and 84 MB key switching keys. Like the entire data within the available 43 MB on-chip memory without the need of writing resultant limbs back to the main memory. So as we have seen earlier, the sequence of operations in key switch. So what happens here is that as we perform inverse entity on a limb, after decomposition, we convert the limbs to coefficient representation. Therefore, in the later stage, when we need to perform inner product with key switching keys, we need to read the decomposed ciphertext limbs in evaluation representation from the main memory. So however, if we modify the data path in this way, the one shown in the right-hand side, we can retain a copy of the decomposed limb to follow the inverse entity data path, and we can also perform inner product with the keys immediately. Thus, we can save many reads and writes to and from the main memory. And another advantage of doing so is that we can fetch the keys for a particular limb instead of fetching all the key limbs at once during the original key switch key inner product step. And next, we perform inverse entity and basis convert operation on the decomposed limb and store it in the dual port memory bank, and go back to perform decomposition to new limb steps on the next limb. And we repeat this set of operations until we have generated all the intermediate limbs for a given denum block of limbs. Thus, we need not write any intermediate limbs to the main memory, and we accumulate all the limbs in dual port memory, avoiding the expensive data access pattern switches. So we mapped FAB to a Xilinx Alveo U280 FPGA in a cloud environment and evaluated its performance. So this FPGA board is a high-end server class FPGA with access to HBM memory. And the overall architecture of FAB consists of 4 key components. First, the host CPU that is attached to the FPGA accelerator board via PCIe, then the RTL design of FAB, which is packaged into a kernel code and it runs on the FPGA. The kernel code instantiates various microarchitecture components as we discussed earlier. And then there are 2 HBM stacks, 4 GB each, that act as global memory for the FPGA board. Then when we compare the performance, the bootstrapping performance, using FAB, we observe about 213 times speed up when compared to the CPU implementation, and about 1.5 times speed up when compared to the GPU. And this comparison is in absolute times, not the clock cycles. And when we compare the logistic regression model training performance, we observe a 456 times speed up compared to CPUs and about 9 times speed up when compared to GPU. Also note that we do not compare the performance of our fab work to other ASIC designs because FPGAs run at a lower frequency and it is hard to achieve the same performance as ASIC solutions because of the frequency difference. To summarize, the performance, cost, and flexibility of fab suggests that FPGA provides a sweet spot for FHE acceleration, and fab significantly outperforms both CPU and GPU implementations of FHE while achieving a balanced design. In contrast to ASICs, fab only uses standard commercially available hardware, that is FPGA, which is highly accessible to the general public through existing cloud infrastructures and can be deployed immediately for under $1 per hour. So by enabling competitive levels of performance within the same availability as a high-end GPU, fab demonstrates that FPGAs are the most viable option for near-term hardware acceleration of fully homomorphic encryption operations. And to summarize both the works together, so through memory-aware design techniques, we propose several optimizations that are feasible with small caches and are agnostic of the underlying platforms, meaning that they can be used in CPU, GPU, and FPGA solutions, and even to build more affordable ASIC solutions. Our fab accelerator demonstrates a practical performance using FPGAs at a fraction of ASIC cost. So thus, both MAD and fab demonstrate affordable and practical acceleration of CKKS-based fully homomorphic encryption computations, justifying the title of the talk. And thank you so much for listening. Any questions?
Yeah, I have a question.
Yeah.
So you mentioned in the short term that FPGA-based FHE acceleration is kind of the most viable solution, but if you're looking forward to the future, imagine a future where FHE takes off. Would ASICs or GPU-based acceleration be a better alternative?
I think it depends on the use case. So for some use cases, FPGA would still make sense. But if you have like very time critical applications, like say, imagine real-time stock trading, right? Then probably ASIC solutions will be more viable.
Okay, any other questions from online? Oh, I think I actually disallow people to talk. So let me enable the chat. Okay, I allow anyone to unmute themselves. So if you have questions. John, I saw you unmuted yourself, right?
Yeah, can you guys hear me?
Yeah.
Awesome. Well, I just want to say thank you again for coming and speaking with us today. This was all really interesting stuff, and I was the one that went over and read through the fab paper, and it was really interesting. I wanted to ask what you thought about possibly incorporating different FHE schemes, and if you've considered doing scheme switching acceleration with the two or any other scheme with CKKS.
So that's a very good question. Like we have an ongoing work, which I cannot talk about more right now.
That's fine.
But we have a work which is going to combine CKKS and TFHE scheme to bring on some improvements to the CKKS scheme.
Awesome.
So that is interesting, actually, you know, how you can leverage the, benefits of each scheme and get a better performance.
Exactly. And there's a lot of interesting ways to go about it.
Yeah.
And
Yeah.
It's nice to see that bootstrapping can be accelerated as it's the primary bottleneck with everything. So this was really cool work, and it was awesome to read.
Yeah, thank you.
No, thank you.
Hey, any other questions from online?
Do you guys have any plans to make that simulator public?
Simulator is actually public.
Oh, it is? Okay, perfect.
Yeah.
Okay, great. So I have one more question. So from
Yes,
the
sure.
talk a lot about the architecture stuff. So my question is about the microarchitecture. What do you think is the most costly part of the microarchitecture? Is it a modular multiplier or something else?
I think it's the modular reduction operation, not even the multiplier. So coming up with a wide modular reduction circuit design, it's the like coming up with an optimized 64-bit modular reduction design is very important to improve the performance of FHE workloads.
Okay. So yeah, maybe one follow-up question. So I guess for example, for the modular multiplication, I assume all the input to those kind of modular operations are already like within the proper range, right? So in those cases, why you need a separate modular reduction rather than, for example, a normal modular adder, subtractor, or multiplier?
I don't think I follow the question. Can you
Okay, so
say it again?
yeah, it's like the question is, what is the use cases of modular reduction rather than modular adder multiplier?
So when you say use cases, are you thinking in terms of other workloads other than FHE?
Not really, just FHE. So I assume, for example, all the input to the multiplier, they are already within the modulus range.
Correct. Yeah.
So why not use, so for example, some optimized modular multiplier rather than optimized modular reduction hardware?
Yeah, so there are cases like when you perform basis conversion operation, right? So you perform modular multiplier followed by so you perform multiplication followed by an addition. So then you don't need to perform modular reduction immediately after multiplication, and you can save on one modular reduction operation by performing modular reduction after performing both multiplication and addition.
Oh, I see.
So that way it makes it more efficient.
Right. That sounds like the Montgomery multiplier. What the Montgomery multiplier is good at, right? When you do that.
Yeah.
Okay. Yeah. Thank you. So any other questions online? If no, let's virtually thank Rashmi for today's talk, and really great.
Thank you so much for the opportunity.
Yeah, thank you so
It was
much.
pleasure.
Super useful. Yeah, thank you. Can't thank you enough for this.
Thanks.
Okay, cool. So
bye.
I will follow up with you later.
Thank you for talking.
Yeah, thanks.
Great. Okay, so I think that's all for today. So yeah, so I'll follow up with you later.
Sure. Yeah, let's keep it this. Yeah.
Okay.
Bye.
Yeah,
Bye.
take care.
Bye, everyone. Bye.
Have a good one.
Okay, so I think that's all for today's lecture. So let's meet after spring break.